Hello, in this video we're going to talk about template arrays, vectors, and catching exceptions. So what is an array? An array is a contiguous group of memory locations that all have the same data type. To refer to a particular location or element in the array, we specify the name of the array and the position. The position is formally called a subscript or index, and it specifies the number of elements from the beginning of the array. The first element in every array has a subscript of 0 and is sometimes called the 0th element. A subscript must be an integer or integer expression using any integral type. So here's an example of an array of 12. So here are the positions. So C bracket 4, C sub 4 is 1543. Let's look at this a little bit more. The position determines which one it is, so you could loop through them. And this is how they are structured in memory. Now, when we declare an array occupies space in memory. To specify the type of the elements and the number of elements required by an array, use a declaration of the form array, left bracket, type, left arrow, left less than, type, comma, array size, greater than array name. The notation type array size indicates that the array is a class template. The compiler reserves the appropriate amount of space in memory based on the type of the elements. Arrays can be declared to contain values of most data types. So we're going to declare an array of 5 variables and run through them and do stuff with them. Okay, so first, what we'll do is we'll say, so we have to include array. Now these aren't native arrays. We're not going to talk about them, but there is a native array type in C++, but it's less flexible and more error prone. So we'll say array of ints, and we'll say there are 5. And we'll call this my array. And we will load values of it. I equals 0. I is less than my array dot size. And this basically says how many elements are in the array, so we don't have to remember a magic number like 5. And then we'll say I++. And what we'll do is we will assign the array equal to 2 times the index. Okay, so now let's print the array. Again, we're going to do the same type of loop. Notice that because we declare it inside the for loop, it is scoped just to this for, so we can use I again. So now we can say array, my array, I equals my array, I. If we run this, it's going to put 0 in the first, 2 in the second, and so forth. So if we wanted to look at the third element, we can say now remember, we start counting from 0, so the third element will actually be in position 2. And if we run it, we will just get this third position. Okay, now, what happens if we do this? Now, if you remember, there are 5 elements of the array starting at 0. We're asking for a 6th element. And we're going to get 0. And this is the array's way of creating a 6th element and it will actually just add one onto the back. Now, that's not how standard C arrays work, C++ arrays work, but since we're not going to be going into them, we can do this too. Now, notice something though. It's not initialized, so we're getting random crap. So, and the problem is that in theory we could just be overwriting stuff, and other stuff may be using that memory, so it's very dangerous to go beyond the ends of an array. But here we can say 7 equals 22, or 9 equals 22, and then if we take our print array, we will see something that might surprise you. You get an error. Why? Because you're trying to access an individual element where there's no memory, because we don't go all the way to 9. Now, if we put in, when we iterate through it, it tries to read the memory at that spot, and it can't. And so basically our code blows up because we're walking to somewhere we shouldn't be. Now, why did this work? Because of dumb luck. There's just nothing in the array we're stopping at. So don't go over the limits of your array is what I'm basically saying. Okay. You can also do a quick initialization of the array using what's called a list initializer. If there are fewer initializers than elements in the array, the remaining elements are initialized to 0 or the default. So here we have 5 in our example. And we could, instead of doing this, we could say, run it. Oops, let's get rid of this error conditions. We run it. All right. Now, what if we do just this? It will only initialize the first 3 elements of the array. The other 2 will be 0. All right. What if we do this? And we're going past and we can't even compile it. So we can now get rid of this, back to normal, and our stuff runs just fine. All right. So we can specify an array size with a constant value when we create it. The code on the right sets the elements of a 5-element array to the even numbers and prints the array. We use a const qualifier to declare a constant array size with value 5. Okay. And then here we use array size. A constant variable that specifies an array type must be initialized with a constant expression and cannot be modified thereafter because we don't want the size of the array changing. Constant variables are also called name constants or read-only variables. So here we just give it a constant instead of putting 5 in there. So if we need to change it, we can easily. So often the elements of an array represent a series of values that need to be used in the calculation. So let's let's just sum up the numbers in our array. Set it to 0. This can also be written as equals 0. And it can also be written as this. All right. So we'll say total plus equals my array sum I, and we want to count sum. If we run it, it will now sum the elements of the array for us. Okay, so we can also show data graphically using a array to kind of create a bar chart. And I'll let you go into this yourself, but it just prints out a nice little bar chart. You can also use separate counters in a die rolling program to track the number of occurrences. So let's take an example. These are functions to help us get a more uniform distribution. And we've got our size t of array 7. So we're going to ignore the 0th element so we can talk about these dice naturally. And we're going to create an array frequency. We're going to initialize to all zeros. So we're going to roll the dice 60,000 times. And for each of the 60,000 times, we're going to get a random integer. And we're going to increment frequency sub-random integer. So if it's a 3, it'll increment the number of 3 counts. And then we can print out all the faces and their total counts. So consider the following problem statement. 20 students were asked to rate on a scale of 1 to 5 the quality of the food in the student cafeteria, with 1 being awful and 5 being excellent. Place the 20 responses in an integer array and determine the frequency of each rating. Now, C++ provides no automatic array bounds checking to prevent you from accessing an element that does not exist. An executed program can walk off the other end of the array without any warnings. Class template arrays each have a function that performs bound checking for you. Here, we can say, instead of we do the same kind of thing. We get an array of responses. Here are our array of responses. And from here, we determine our ratings and print them out. But we also use size to limit the number of elements we look at, because without it we can go off the end of the array. So, ensure every subscript used to access an array is within the array's bounds, greater than or equal to 0 and less than the number of elements. Allow programs to read from or write to array elements outside of bounds are common security flaws. It's a way people can hack your code. Reading from out-of-bound errors can cause a program to crash or execute incorrectly with bad data, and it can seem to happen at random times. Writing to an out-of-bound element, a buffer overflow, called a buffer overflow, can corrupt the program's data in memory and can crash an entire system and be used to hack the system. So, a program initializes static local arrays when their declarations are first encountered. If a static array is not initialized explicitly by you, each element is initialized to 0 if it's the appropriate type. Local variables are something called automatic variables because they're automatically destroyed when the function finishes executing. So, here we could we have a function prototype static array in it, an automatic array in it. And here we can make a first call to each function and a second call. And here we create a local array. And the values on entering the statement should all be zeros. And then we're going to modify them to here and output them. And with a local automatic array, it is just local and it's not visible outside of the current array. So, a range-based for statement. It's common to process all the elements of an array. The range-based for statement does this without a counter. It makes it simpler and you can't step out of the boundaries. The array and eliminating the need to implement bounds checking. So let's do a simple range-based for. Also referred to as for each, because you do something for each element in the array. And here, let's take an example. So, for int item in my array, and it's that simple. run it. And here, it walks through our array and prints every element, and boom, we don't have to do anything more. Okay, here's a similar example. Now, if we want to change the actual item, we can pass in a reference, start with a reference variable, and therefore it points to it and we can reference it. So, let's create this again, but this time we'll use a reference. To an integer, so it means it can be changed. So and now let's print it out again, but let's use some of our old code to actually just print out what's in the array, so we can see that it changed for each of them. And notice we now have much bigger numbers. So, range-based statements, you don't need the element subscript. It can be used in place of a counter-controlled for statement whenever looping through the code does not require access to the element subscript. So if you look at here, we can't say which element this is. So if you need to know the exact element at the time, you need to use a normal for. If you need to use subscripts, then you're going to need to use a counter-controlled for statement. So, basic searching. It's common to have to determine whether an array contains a certain key. This is called searching. The simplest approach is called linear search. So, here are two ways to implement linear search. We can use a standard for loop, find the array 5 values, find the value, and return the value, or return the position. Or we can return the actual, whether we found it, true or false. The standard loop returns the position of the item. Enhanced only returns existence. When we pass the arrays to functions, we must provide the exact size. This is trouble for arrays of different sizes. When we discuss vectors, you will see why vectors are almost always a better choice. So, now we have multidimensional arrays. You can use arrays with 2 dimensions, i.e. 2 subscripts, to represent tables of information arranged in rows and columns. You can even have more subscripts if you want. To identify a particular data element, we must specify 2 subscripts. The first identifies the row, the second identifies the column. They're often called 2-dimensional arrays, or an array of arrays. Arrays with 2 or more dimensions are called multidimensional arrays. So here is a visual. Row 0 is represented by A sub 0, 0, and row column 1, row 0, column 2 is A sub 0, 2, and so forth. The row subscript comes first, and then the column subscript after the array name. So, we could demonstrate initializing 2-dimensional arrays. We have an array, which is an array of int, and it has the number of columns as its column, and then the number of rows as its rows. So it creates a square array. Okay, and then we have array 2, which does the same. Now let's create this code, so you'll see what it looks like. Let's see. So we will. Let's count all this out. First, we'll create a method print array, and print array is going. We'll create. First, let's define constants. 2 rows and 3 columns. Okay, and then we'll have our function, which takes our function prototype. So we'll say void print array, and we're not going to change the array in here, so we're going to make the array constant, our multidimensional array. But it's an array, And its elements are an array of ints and with a size of columns. And I used autocorrect in my chair, int of size columns. And that it is itself an array of size rows. So now we'll call this guy, well, we're just going to pass in a reference to this so we can change it if we want. All right. So now we will add our function itself. And use the same signature. An array of arrays of int columns. Rows, and we'll call this, and we want it to be a reference, and we'll call this table, and we'll say now, what does this auto do? Auto basically says, well, we already know the type of row. We can assume it because table contains rows of rows. So it'll create a constant of type, I mean an array of the inner type. So we can traverse, this is called an array of the outer type, which has elements of the inner type. So now when we're in here, we can say we want to use the array of the inner type. And this time, this should be, oops, I got space here. And this is in the set of rows. So this pulls a subarray of each of these. There are row numbers of arrays of ints. And that's what each of these is. In fact, we could replace the auto with this. Okay. And we could replace this auto with this. And make it a little clearer to understand. We can see out the element. All right. And so it's going to print out the elements in a row. And after we print each row, we're going to throw an endl so it prints a new line. All right. And then let's come back up to our initialization code where we're going to set up our array. First, we're going to declare an array of arrays of type int, column, and type rows. That's how many we want for our elements. And we'll call this array 1. And we're going to actually initialize it to 1, 2, 3, 4, 5, 6. Oops. And the way this will lay it out, you'll see in a second. And then we're just going to print our array. Oops, typo. Notice that it just linearly fills in our array. Our array looks like this. It'd be row 0, column 1, 2, 3, row 1, column 4, 5, 6, and it just fills them in linearly. You could also do this. Let's create another array. This one we can be a little bit more explicit with. We could say array 2 consists of what we're going to spell out which is in which array. And we'll say this is and let's not print this guy. Now, this second form shows explicitly that this is an array of an array. So to process multiple dimension arrays, we need a nested loop where the outer loop iterates through the rows and the inner loop iterates through the columns. The auto keyword tells the compiler to infer a variable's type based on the type of the variable's initializer. We could also do this with a counter-controlled iteration as follows, where we have the row and the column specified explicitly using a normal for loop. So, there are some problems with the arrays. Number one is having to know the size and not being able to change it. C++ defines a library called the Standard Template Library. The Standard Template Library has an item in it called a vector. A vector is like an array, but also supports dynamic resizing. Except for features that modify a vector, the others seen earlier also work for arrays. It's defined in the header vector and belongs to standard. By default, all elements of a vector object are set to 0 or null. Vectors can be defined to store most data types, and size obtains the number of elements in a vector. You can use the bracket operator. You can have vectors and vectors. However, when you pass arrays as parameters, vectors as parameters, unlike arrays, you don't have to give the sizes, which is nice to make more generic type routines. So let's take some examples, and we'll create some methods here. Let's put this in a separate function. We'll call it print vector, and this will take a vector of int vector and print it out. Now it's complaining because we haven't included vector. All right. Now we'll say is for int item in vector However, you shouldn't do this. This is a bad name. All right, we'll take our prototype, we'll throw it up top so it'll work, and then we will initialize our vectors. First, let's create a vector. By the way, we don't need this. Here we define our new vector of type int, and we'll call it v, and we'll set it equal to 1, 2, 3, 4. And then we've already defined our print vector. Let's go ahead and run it. And there we go. We can also now change individual items. We can say vectors 3 9. Print our vector again. And see what we get. Oops. Sorry, this should be V. And this time when we print it, we will change that last item to 9. Also notice that when we output a vector, we can pass in a reference just like before. And notice size is a function here. Oops. We can use square brackets as well, just like with a normal array. We can change the size of an array by pushing to the back of the vector 1000. That'll automatically change the size of the array. So let's say, for example, here we want to add an element. We say vector.push back. Oops. We'll say 5. And then we'll print our vector again. And now if we run it again this time, we'll print out our array again. And now there'll be 5 entries. Very easy to add additional items when we need them. Okay. When we want to use an object constructor, we can specify the size, or we don't have to if we can initialize it directly. So, yeah, that's about the one we show to that. You can use inequality to compare vectors. And this code, by the way, is listed in some of the samples. And yeah. So that's kind of the overview of vectors. They're very much like arrays, but you can assign whole vector objects. You do have to do bounds checking when accessing elements with squares, with square brackets. And there is a bounds checking function in both vectors and arrays called @. So instead of saying v bracket x, we can say v.at and then pass in a parameter of an index. And if that's out of range, it won't blow up. So what is exception handling? An exception indicates a problem that occurs when a program executes. The name exception suggests that the problem occurs infrequently, and it should be that way. Exception handling enables you to create fault-tolerant programs that can resolve or handle exceptions. When a function detects a problem, it throws an exception, and essentially an exception occurs. To handle an exception, we place code that may throw an exception in a try statement. The try block contains code that might throw an exception. The catch block catches the code, and it handles the exception. You can have many catch blocks to handle different types of exceptions that might be thrown in the corresponding try block. Uncaught exceptions bubble up to the caller until they are caught or they terminate the program. STL provides a class specifically designed to declare objects to be thrown as exceptions, and it's called standard exception, and it's defined in exception. This class has member functions we can redefine, and we'll explain that later, and return an appropriate message for the exception. So here's the general pattern. Try some code, catch type of exception, and handle it, catch type and handle it, or a catch all. And this will catch everything. Catch ... A try statement can have multiple catches for different types of errors, and it goes from most specific to least. You can also throw exceptions yourself to get other areas of the program to handle it. So let's take an out of bounds exception. Right? Let's create this array and try to access the out of bounds. To demonstrate exception handling, we're going to create a new piece of code to keep it clean. And what we're going to do is we're going to define vector v, and then, oops, forgot my type here. Let's call it char. This will be different, or even a string is really different. And we'll say e.add push back, which will add our item at the back. Okay. So now our vector should have one item in it. So now we're going to try accessing it. We're going to put our try text block. Try, and we will say count v.at, because it does bounds checking. So 2. And that should give us an error message. So if we run this without the try catch, it's going to blow up. Okay, because it throws an instance of standard out of range exception. So what we can do, put our try block, try this code, and when it fails, we'll say catch out of range. We always use references for exceptions just to keep the memory footprint smaller. And here we can say out of range attempt. If you want to see what actually happened, you can use the what method on the exception class. So now if we run it, it doesn't blow up. It just says we get this out of range attempt. Okay, so this is very useful. It allows us to control when things go bad. Now, what if we have a different type of error? Let's see. It will catch an integer exception. Okay, so we raise that one on our own. Coming back to here, we can throw and catch our own exception, and that covers the basics of exception handling. So basically what it is we do a try and a catch block, and if our error issue throws an exception, it will cause an exception to be thrown, and you then just need to catch it and do what you would do to repair the state, and then it will exit the method. If you don't have a catch, it'll throw it up to the higher level method, and if it doesn't catch it, it can eventually lead to terminating the program. And you can have, there's all sorts of different type of exceptions defined in a standard namespace.